0.2. Okay? So that tells me that I'm 3.2 standard deviations above what we expect. If you look 3.2 up in the back of the book, in table E2, 3.20, you're going to see that my sample, the probability of doing worse than my sample is 0.99931. Or there's a 99% chance that if I were going to repeat my sample, it would be less than 20. Which means this area, this very small area right here, means that if I were going to repeat my experiment, the probability of getting over a 20 again is less than 1%. It's actually 0.00069, or 0.069%. So 0.069%. Very small chance of getting greater than 20 if I repeated this experiment randomly. Okay? Now, the final thing you'll see in Chapter 7 is sampling distributions for proportions. And I just want to briefly touch this because we're going to look at it much more next week. But sampling distributions for proportions, same thing. What's a proportion? Okay, proportion, percent, or ratio. 60%, 3 out of every 5, 60%, 6 out of 10, proportion, percent, ratio. So, for instance, if I say, do you support government health care? Yes, no, yes, no. 1 for yes, 0 for no. 6 out of 10 Americans support government health care, something like this. So, proportions. You hear it a lot in elections. Do you support Obama, yes or no? Do you support McCain? We just heard about approval ratings for the president, and they're going down as the economy gets worse. So, proportion, percent, ratio. The reason we treat these a little different is because you cannot have more than 0%, you cannot have less than 0% rating. Which means, if I were elected president, I could do no worse than 0% approval rating. Conversely, I could do no better than 100% approval rating, which would be very hard to do, but so it's bounded. Now, if we're doing means, we can have an average temperature over 100 degrees, which would be 45 degrees Celsius, but over 100 degrees Fahrenheit. We could, sure did. We had it this summer. But we could also have an average temperature, as we do in Ohio, less than 0 degrees. So we're not bounded. In fact, it could go either way. Percents are not bounded, right? So we have to change our formula a little bit because our z-score formula changes just a little bit. Pretty much, we call what we expect that there are maybe 50% of people support government health care, and then so we call that capital P, and then we sample. And so capital P is population proportion. Our sample is denoted by p hat, sample proportion. And this is a statistic, just like x bar. This is a statistic. So it's kind of our second statistic and the second most important statistic we will work with. And standard deviation, it doesn't change either. I mean, we still have standard deviation, but it changes just a little bit to p 1 minus p over n. And I'll explain that, and you can see that in section 7.4. In section 7.4, you can look at this. Now, your book uses the symbol pi. Pi also means percent. But oftentimes I notice that students use this 3.14 for pi, the number pi, not the symbol pi. Okay? Pi has a different mathematical meaning. In statistics and math are different disciplines, but pi has a different meaning in math. So I substitute pi with p. Pi is just the Greek letter p. Okay, so we will substitute the American p, or the Latin, excuse me, the Latin p here in our standard deviation formula. So it's p times 1 minus p over n. So if we said p is population proportion 50%, and I will write that 0.5. 0.5 or 50% of the country supports government health care. Okay? Then I expect my sample proportion, my p hat, I don't know what it will be, but I'll go collect it, and the way I find it, again, is number of successes over number of trials. And as we spoke last week, successes doesn't have to be positive. And in a very morbid way, number of successes could be cancer patients. Okay, so if you were looking at a Mountain Creek and those who live on Mountain Creek Lake, in the percent of people who get cancer, they're with eating with the water being close to the power plant compared to those who live other places in the Metroplex. Okay, that could be a study. Well, this is how we get p hat. So number of successes over trials. Here, government health care. Number of successes, who supports it, over number of trials. How many people I asked. So let's say this would be 49 out of 100. Okay, so my p hat would be 0.49. Simple. My standard deviation is p, 0.5, times 1 minus p, which is also 0.5 over 100. Okay? All under the square root. And this is my standard deviation. Okay? Nothing else about the distribution changes. So, once I get a standard deviation, once I have my p and my p hat, I can do a z. Now my z-score is just 0.49 minus 0.5 over 0.5 times 1 minus 0.5 over 100. In symbols, this is p hat minus p over the square root of p times 1 minus p over n. Now, this p, and this p are the same p. Okay? So, in our formula, 50%, 50%, 50%. 0.49 over to standard deviation. So, on the top, we have z equals 0.1 minus